Thank you all for joining this fourth annual of the International Day of Women in Statistics and Data Science Conference with this year's theme, Thriving in Your Environment. We're recording the event and the videos will be available at the Caucus for the Women in Statistics YouTube channel. We kindly ask you to post your questions to the speakers in the Q&A chat. And without further ado, I am delighted to host this session, 310, Brazilian Women Thriving in Research, and to introduce our first speaker, Daiane Zoanete. So I'm going to stop sharing here so Daiane can share her screen. While she does that, Daiane holds a bachelor's degree and a master's degree in statistics from the Federal University of São Carlos and a PhD in statistics from the Interinstitutional Graduate Program of the Department of Statistics of the Federal University of São Carlos and the Institute of Mathematics and Computer Science at the University of São Paulo. And she's currently the president of this interinstitutional graduate program. She's a member of the International Network for Research and Public Policy. She has worked in the area of probability and statistics with emphasis on selection and estimation of independent or dependent mixture models, QTL mapping with familial dependence, parametric and non-parametric Bayesian inference, and MCMC computational methods with applications mainly to genomics and molecular biology. So thank you so much, Daiane, for accepting our invitation to speak here at the event, and please go ahead.
Hi, everyone. Can you see my slides?
Yes, perfectly.
Yes, thank you so much. And so I would like Gabriela so much for the kindly introduction and also for the invitation to be a speaker in this event today. I chose to talk a little bit about this subject because it's a joint work with Mariela Bogoni, who is one of my former master's students. And we decided to study a bit about the variable selection methods, in particular Bayesian methods, because they have been studied and discussed so much in the last decades. And if it's possible to select a subset of real relevant and important covariates in a regression model, it had improved the model prediction, it had improved interpretability, reduced complexity, and also had avoided the overfitting and multicollinearity. Especially when we consider mixture of regression model, variable selection, it's a more complex problem because you need to select variables, not just for one model, but we need to select variables inside each subgroups in the population. So our goal here is to present Bayesian methods for estimating and also selecting variables in the same time for a mixture of logistic regression model. Here we choose a Bayesian perspective. So we need to simulate sample from the posterior joint distribution of the model and consider logistic regression model, even if we choose the normal prior distribution for the regression coefficient. It's not simple to simulating from them because we don't have a conditional posterior distribution in a closed and when in a well-known distribution. So we want to also augmentate the data using polygamma random variables to make the simulation more easy for this model. Here we just have the definition of a finite mixture of logistic regression. So you have a random sample from a population with K subgroups. And as we don't know from which subgroup each individual or observations belong to, we define these marginal distributions for each individual. So here we have the vector P that represents the weight and the frequency of each subgroup in the population. And here we have a binomial distribution for each individual. In a regression model, we can write the success probability for each individual J inside each subgroup I as a function of covariate. And here we assume the logistic link function. That's the most popular link function for a logistic regression. So here we want to select variables, the most relevant variables inside each I subgroups here. It's known that if you use the marginal distribution of a mixture model in our likelihood function, it's not computationally efficient. So we usually augmentate the data and add some discrete non-observed variables, as S, for example, one for each individual. And this non-observed variable represents from which subgroup each individual belongs to. It's not an observable variable, so we need to predict it inside our estimation process. So we can rewrite the likelihood function in this way. Consider that the individuals are independent among them. So as parameters, we have the P vector, and we need to estimate this. And we also have as parameter the regression coefficient, the betas. Note that we have a vector of betas for each I subgroup here. Consider a Bayesian estimation process. We need to assume prior distributions for this P vector. Usually it is a Dirichlet process, it's a conjugate prior for this parameter. And for the betas, we usually assume a normal distributions, prior distributions for them. But even assuming a normal prior distribution, that's very common, the posterior conditional distributions for them, it's not in a closed and well-known formula. So usually we need to use the metropolizations to simulate samples from them that could not be efficient or scalable. However, in 2013, Polso and collaborators suggest a data augmentation strategy to facilitate the sampling procedure. And add, in the logistic model, regression model, the polygamma random variables. The main result says that this left size equation here can be written as a function of a polygamma random variable. Here he is represented by W variable, and also a function of the standard polygamma density distributions. So you can notice that this left size expression, it's very similar, has the same structure of the binomial likelihood we can see here in the equation number 3. And if we replace this expression for the right side of that equation without integrating out the polygamma distribution, we can achieve a well-known and closed posterior condition distributions for beta. So here, we just replace in the likelihood function the kernel of the binomial distribution for the representation as a function of polygamma distributions. And the likelihood function can be written as in the second part of the expression. You can see in the first part, we have a expression very similar to the kernel of a multivariate normal distribution, and only this part of the expression depends on the regression coefficient. The second term here does not depend on the regression coefficient, and only depends on the polygamma random variables. In this way, if you combine this new likelihood function with a normal prior distributions for the beta, we can get a conditional posterior distributions for them in a closed and well and non distributions as a multivariate normal distributions, and you can easily simulate from them. Of course, we also need to find the posterior condition distributions of the polygamma distributions, but you can show it also a polygamma distributions. So we can estimate this model, a mixture of logistic regression, using just a Gibbs sampling MCMC algorithm, and in each step of the MCMC, we just simulate from distributions that we know, and it's easy to simulate from. Example, the Dirichlet distribution, multivariate normal distributions, and the polygamma distributions. And it makes the estimation process more easier and scalable. In fact, to include variable selection in this estimation process, we augmented the data again, including the latent variables gamma here. We add a gamma variable for each covariate inside each subgroup you have in the population. And it's just a binary variable. This variable assumes the value equal to 1 if the covariate associated with it is relevant and has a beta different from 0. And this gamma variable assumes a value like 0 if the associated covariate is not relevant and the beta associate is equal to 0. So the selection variable, the variable selection procedure is just an update of this gamma variable. We need to update it and see if it's equal to 0 or equal to 1. And you can update this in MCMC algorithm using the condition marginal posterior distributions of the gamma. This PIT, it's the prior probability I give for this each gamma variable, and you multiply it, combine it with the marginal likelihood of the data. Just because we include the polygamma random variables in the model, this marginal probability here can be found in a closed and well-known expression given here in the equation number 6. Okay, so our process is just to update all these indicator variables gamma. If it's equal to 0, we set the associate beta equal to 0. If the gamma is equal to 1, we associate a prior distribution for this beta and sample a value for it using the conditional posterior distribution of it. Some common priors for making include variable selection is to assume a prior normal distributions here for this beta. Just for the beta, which has a gamma variable equal to 1 associated with this. This is another way of to write the Spike's lab prior that it has becoming very famous for variable selection. But you can also assume another normal prior distributions for the beta with this special variance here that you also consider the data to be defined. And this formulation it's known in the literature as G prior distributions for regression coefficients. So here I will show, because of the time, just the results of the real data set and compare Spike's lab and G prior for the variable selections here using the polygamma data augmentation to have MCMC procedure more efficient. Our data consists almost of 400 students, and we observe for them the final grade for a math exam. They are students for Portugal. So the exams had 20 questions, and the response variable is the number of questions that were correctly answered by the students. So the response variable varies from 0 to 20 and has a binomial distributions. For covariates and predictor variables, we had almost 70 covariates available, such as age, gender, weekly study time, mother's and father's education, and many others covariates. For this data set, we run the spike and slab prior and also the G prior distributions with different numbers of subgroups and using EBCI and also DCI selection criteria. We choose 2 subgroups inside this sample, inside this data set. And here we have the bar plots that can describe the subgroups. The first subgroups, we call that they describe the average performance. We can see we have individuals that are not 0 grades and not very so good grades in the math exams. And the second group, we just have students with extreme performance, or students with 0 grade, or students with very great high grade. And here we have just the subgroups of G prior distributions model, because we observed that the results were better than the results of its spike and slab. And here, just to finish the presentation, we have the variable selection results. And we can see for the first group, we have many covariates selected, and they make sense with our goal. For the second group, C2 here, that just separate the very extreme performance, students who have very low or very high performance, we can see the method didn't select so many variables here, and it may make sense in sometimes, because if the students are so good or so bad, it's a natural feature of him, and the covariates maybe not so explain this phenomenon. Okay, thanks so much for the presentation. Here I have the paper with more details about the calculation, simulation, and real application. And you have also here my contact, my email, and you can be in touch anytime. Thanks so much.
Thank you so much, Diane, for the insightful presentation. It was very interesting. I see that we don't have any questions at the Q&A chat. Please, if you have questions for Diane or for the other speakers, please put them on the chat. I'm going to go ahead and introduce the next speaker for the sake of time. So our next speaker is Kelly Gonçalves. She's a professor at the Federal University of Rio de Janeiro in the Department of Statistics. She has been a visiting researcher at the Department of Statistics at the University of Florida in the USA. She's also a visiting researcher at the Institute for Applied Economic Research, IPEA, and the technical consultant for a cooperation project between the Brazilian Institute of Geography and Statistics, IBGE, and the United Nations Population Fund. Currently, she's a CNPq Productivity Fellow and a Young Researcher of FAPERJ Fellow. She also is part of the editorial board for the Brazilian Journal of Probability and Statistics and Spatial Temporal Epidemiology. And she's also the current president of the Brazilian chapter of the International Society for Bayesian Analysis. So Kelly, thank you so much for accepting our invitation to speak here today, and go ahead.
Thank you, Gabriela, for the invitation to be here. It's a really pleasure for me to be here. Today I'm using the Wonder Woman quote, because only being a Wonder Woman to conciliate the work with the motherhood and domestic tasks also. So thank you very much, everybody, for being here. So this work that I will present you today is related to a research project funded by Brazilian Research Funding Agency. In this presentation, I will discuss the work carried out by 2 master's students in statistics at Universidade Federal do Rio de Janeiro, where I work as an associate professor. Both students were supervised by me and Denise Brits, that was in the previous session. Particularly, the second thesis, second dissertation was also co-supervised by Professor João Pereira, that is a colleague of my department. As part of the work was developed by the student during my maternity leave. Okay, so this work is now giving rise to papers that are currently in preparation. So we are talking about our main motivation are the Sustainable Development Goals. So the Sustainable Development Goals were adopted by United Nations in 2015 as a universal call to action to end poverty, protect the planet, and ensure that by 2030, all people enjoy peace and prosperity. So I'm presenting here and sharing my screen here. So I will look to both sides, okay? So as we know, we have 17 SDGs. They are totally integrated. This is an action in one area would affect outcomes in other areas. So in this work, we are particularly interested in goals 1 and 8. Goals 1 mean no poverty, and goals 8 aims decent work and aspects of economic growth. Okay. So the SDG agenda has driven the production of data and the adoption of new methodology. This is the use of reliable statistics is essential for assessing progress towards the SDGs. And in this work, we are particularly interested in goals, as I said before, in goals 1 and 8. Okay. And it requires appropriate data sets and methodology. Particularly because we can use surveys to create indicators to monitor these goals. Actually, household surveys often result in small sample size for specific demographic or geographic groups, making direct estimation unreliable. What I mean with making direct estimation. Direct estimation is the estimation based on sample data alone. So we can also look for disaggregated statistics by characteristics like income, sex, age, geographical location, because disaggregated statistics would provide more complete information and give a better overview of the situation, country situation. Localized data on issues like poverty or food insecurity or health allows countries to develop target programs and can allocate resources effectively to specific communities. Okay. So the overview is that surveys often cannot estimate all quantities of interest through direct methods with acceptable accuracy. What I mean with acceptable accuracy, this is we'd like to use indicators that have a good level of precision. Okay, so small estimation methods could help us in this task because they use other databases through statistical models to solve or at least mitigate this problem. So improved estimates for these areas are obtained by borrower strength from similar other areas. Okay. So what I mean with small area is a domain. It's not specifically a small area, but a domain where sample size is not sufficiently large to produce reliable direct estimation, to produce good estimate with good precision. Okay, so talking about the methodology, you have 2 types of models. Basically, the area level model and the unit level model. In this work, I'm going to show you the works with area level model. In area level model, we use aggregated auxiliary information at the area level, and unit level model, as its name, work at the individual unit level. The second one, it would give us more detailed prediction, but we need this disaggregated information that could be a hard task. Okay, so the first one is the most, in general, the most used methodology. The success of the methodology is related to the covariates that you use to explain your direct estimates. So look for the right covariates is very important. So you would like to have a covariates that covariates that are correlated with the outcome indicator. You can use in this task the expector's opinion, and you can use auxiliary data source. So, for example, administrative required census or the same server but on a different year. Okay. So in the work that I present here, the students have a lot of job looking for this right covariate. So as I said before, the first motivation of this work is represented by Goal 1 of SDGs. So Goal 1 means end poverty in all its form everywhere. To talk about this goal, we need to define the statistical indicators. So you could use poverty measures. They are well known in the literature. So here I have a general expression for you for the poverty measure. So you can see here that the poverty measure compares the per capita household income for individual J to the poverty line. Okay, so the poverty line is the minimum income level considered necessary to basic necessities like food, clothing, okay, and others. Here we have also, as I said, Z is the poverty line, and N is the number of people in the population. And this part here is the indicator function that assumes value 1 if Yj is below the poverty line. Okay, so you can see that this general expression depends on alpha. Develop alpha will give us three types of measures. The first one, when alpha is equal to 1, we have the incidence of poverty. That is our headcount index. It gives the proportion of people, the people living below the poverty line. The second one, when alpha is equal to 1, represents the poverty gap. It's a measure that quantifies the average income shortfall of the poor from the poverty line. It's also expressed as a percentage of the poverty line. And the third one, when alpha is equal to 2, is the poverty severity. It gives more weight to those with greater poverty gaps because we make the square of the gap. Okay, so this measure would penalize more deeper poverty, okay, more heavily than shallow poverty. Okay, so in the first work we deal with these three main measures. I will not have so much time here to present to you, but I give you idea of the work. So for Brazil, we can use this as a statistical data source, the Brazilian National Household Survey. Also, reliable state-level poverty measures can be obtained from this survey. The production of spatially disaggregated statistics could be helpful for decision makers and would requires small error estimation. So our job was use small estimation to improve the precision of the estimates. So particularly our aim is to produce poverty estimates for geographic areas smaller than states. They are called geographic strata. Denise talked about this a little bit in the previous session. Okay. So in Brazil, we have 146 geographic strata. They are composed of groups of municipalities with some similarities. Direct estimates can be produced, but they need to be used with caution due to the lack of precision. We have some geographic strata that have estimates that have a low level of precision. Here I show you a map with the spatial distribution of this poverty indicator. Okay, and the right panel is the most important for us. Here we have the coefficient variation of the estimates. So you can see some geographic strata with real large coefficient of variation particular, here I bring you a summary of the scenario. We have 114 of the 146 estimates of poverty incidence with a coefficient variation CV above 15%. And more serious, we have 32 geographic data with estimates with a CV above 30%. So this one could need to be used with caution. Okay. So in our work, in the work of Maria Eduarda Gala, our students that were supervised by me, and Denise Brits, she worked with models, a model-based approach with the motivation to of producing better estimates with a lower precision than those obtained by direct estimate. Okay, direct estimation. So here I do not have time to detail for you the methodology, but we used a beta model since the indicator below the interval 0, 1. Okay, so theta hat is the direct service estimator of poverty measure. In our case, we worked with the 3 measure, the poverty incidence, the gap, and the severity. And our aim was to estimate theta E, the true parameter, with a good level of precision. This is reduced coefficient of variance. And Maria Eduarda worked a lot looking for the right covariates. And in the end, we worked with social variables, education, economic covariates, and we test some models varying these right covariates. The second problem was, as I said before, motivated by the goal weight of SDGs, where the aim is to promote sustained, inclusive and sustainable economic growth through and productive employment and decent work for all. Okay, so motivated by this, and we use it it's natural to think in these statistical indicators. This is the proportion of unemployed people, the proportion of employed people, the proportion of economically inactive people, and it's natural to also estimate the employment rate. Okay, so as I said before, we're dealing with our other level models, model estimation based on our level model. So in this case, we have a vector of proportions. So it's natural to use the Dirichlet model to model the direct estimates in this case. Okay. I forgot to talk a little bit about the model. You can see that the model depends on the covariates here and the area random effect. Okay, so it's like a classic type of area level model. The same would happen in the Dirichlet model. That is the natural choice for a vector of proportions subjected to a unit sum constraint. That is the case of the proportions here used for SDG 8. Okay. We also use the statistical data source, the Brazilian National Household Survey. Here we have in the left panel the special distribution of the unemployment rate, okay, estimates. But the most important here is to look at the coefficient of variation of these estimates. So here we have legenda with the level of precision, and we can see, for example, that some geographic strata have estimates classified as imprecise or with a low level of precision. Here, I bring a summary for you. The level of precision classified as moderate or inferior happens for 55 out 146 geographic data estimates. Okay, so for these places, we recommend the use with caution. So the second student, Luisa Arce, she worked with the production of improved estimates. Actually, she worked, as I said before, with the Dirichlet model, since we have a composition of vector of direct estimators. Okay, so we worked with the Dirichlet model, This is the direct estimate. Our aim is to estimate the true parameter represented here by mi, okay, associated to each proportion. So in this case, we have k equals to 3, okay. Here's the random area effect. And this is a Dirichlet model, a traditional model, using this more estimation that can be used in this scenario of more estimation. Okay, so as auxiliary variables, she also had a lot of work to find the right covariance, as I motivated before. So she worked with social variables, demographic variables, educational variables, okay, and tested, and also economic variable, and tested the performance of the models using some of these auxiliary variables, all of them, and tested and compared the models. Okay. So I do not have so much time to show you the results, the details of the methodology, but I can tell you that in both applications, the models produce poverty and labor force estimates in Brazil with a better precision, and that's important, no evidence of bias. So we think that the work was an important contribution, national contribution. So thank you very much for the audience, for being here, for the attention. I'd like to thank also Fundação de Amparo à Pesquisa do Estado do Rio de Janeiro, FAPERJ, for financial support. If you want to talk with me, if you want more details about the work, you can send me an email. You have my mail. If you want to see my work, my publications, or anything else, you can see my website. Here I bring you also the website of the graduate program in statistics at UFRJ, where I work. And here I also bring you the Instagram of the Department of Statistical Methods of the university where I work at UFRJ. So you can see also some interesting things there. Thank you very much.
Thank you, Kelly, so much for your presentation. It's very interesting that it really ties in together with what Denise was talking in the previous session, and at least it made me want to learn more about this, or probably look at the papers in the future. So thank you so much. Since we don't have any questions in the chat, I am going to go ahead and call our next speaker, Tayane. So Tayane Praz, could you please go ahead and stop sharing so Tayane can start sharing her screen? Tayane Praz is a professor at the Federal University of Rio Grande do Sul. She holds a master's and a PhD in mathematics, both with emphasis in probability and mathematical statistics. She has worked as a data scientist at StatSoft South America, and is currently a permanent member of the graduate program of statistics at the Federal University of Rio Grande do Sul, where she's a professor. Currently, she's a CNPq Productivity Fellow. She has experience in the field of mathematical statistics, focusing primarily on the following topics: time series and nonlinear stochastic processes, long memory models, imputation of missing data in time series, and she's also the main developer or contributor to a growing series of R packages. So Tayane, thank you so much for accepting the invitation to speak in our session, and please go ahead.
Thank you, Gabriela, for the warm presentation. Thank you for inviting me for the session. And I will be talking about imputation and the effects of imputation on estimating the FA and the CCA coefficients. This is a joint work with Guilherme and Alison. It started as Alison's undergrad final project and then became his master thesis. Guilherme was his co-advisor. So I will show you a little bit of our research. So missing data is a very common and challenging problem in several areas. I brought you some examples. For instance, in finance, a very small network glitch of only 30 seconds can cause a really big gap in stock prices if they are being recorded in a high frequency approach. In environmental sciences, a sensor that fails for several hours due, say, to power outage can cause data loss. And in medicine, say, if a patient heart is being monitored and the monitor is temporarily disconnected, it will create a gap in the measures. It doesn't mean that the heart is not beating, just data is not there. And same in the other cases. And analyzing this data becomes challenging if you have to take in account that the data is a time series and there exists correlation between the observations. So some techniques cannot be applied directly to data with gaps. Especially when we are talking about the trended fluctuation analysis and the trended cross-correlation analysis that are very common methods applied to understand, to study the joint behavior of time series. We cannot apply these methods if the data has any gap. So we would like to complete the data somehow, and so a natural question rises, that is how different imputation techniques will affect the estimates of these quantities. And our goal is to find the best way to handle missing values, preserving the underlying correlation structure in the data. So we started with a very small task that was evaluate the performance of traditional imputation methods and compare these methods with CART, which is a decision-based decision tree method. This was the Alison's undergrad final project. We wrote a paper with our results, and we described the difference and how different methods perform. Then, as his master thesis project, he compared these methods with probabilistic regression trees. We made some modifications so the algorithm could be applied when there are missing data. We proposed this modification, and we are now publishing a paper about it. To explore the behavior of the CCI and the DFA functions in the presence of missing data, we performed some simulation studies, always assuming that data is missing completely at random. That's the most simple scenario, most simple mechanism to study. So we had 5 main questions, which were: which imputation method presents the best performance in terms of mean square error? Which imputation method will lead to estimates for the FA and DCCA closer to their expected values, which were derived by me and Pumi earlier? Other question is, do the best performing imputation methods in the first and in the second items, do they coincide? Are they the same? Better imputation means better estimation. And does the dependency structure in the data has any influence in the results and the proportion of missing? So we had these 5 main questions which we aim to answer. So to understand where the trended fluctuation analysis and the trended cross-correlation analysis fail under missing data, let's just have a basic idea of how these quantities are estimated. So we start with, say, 2 time series. Here I have a figure for one of them. Here only 11 observations, so it's easier to observe. So imagine you have a single time series. You first compute the integrated sign. It means you have to compute the cumulative sum. If you have a missing data, how do you do that? If instead of, say, the second observation, there is an empty space, you cannot compute this cumulative sum. So you need to complete this data somehow. Well, once you obtain this integrated signal, you just divide this in n minus m windows of size m+1. And for each one of these windows, you fit a polynomial, usually degree 1, but you can use higher degree depending on the structure of the data. Once you have the polynomials, you compute the error term for each window. You have then a vector of errors. You can compute the variance and the covariance for the residuals in each one of these windows, and just take the mean for the variances and the mean for the cross covariances, and you have the coefficients which we are talking about, which is the DFA and the CCA. Then you can construct the detrended cross correlation coefficient, which is the equivalent to the Pearson's correlation, but using the detrended quantities. What we know is that under short range dependence, these quantities will behave as multiple of m, while if there is long range dependence, either long range or long range cross dependence, this will behave as m at the power alpha, say, and this alpha is related to the Hertz coefficient, which measures long range dependence. So as imputation techniques, we consider classical methods which are implemented in the IMPUTS package. Here we selected only 5 of them based on our previous work. And we also compared these methods with 3 based methods, which are the CART and PR3. This last one is implemented in a package first wrote by Alison, and then now I became the main maintainer. We just released the new version, 2025, which is much improved version of the original package. So these methods, 3 based methods, they will use neighbors values for the missing value to predict that point that's missing. So our covariates will be say xt -1, xt +1. To understand or to answer our questions, we performed an extensive Monte Carlo simulation study. We considered 10 different scenarios regarding this 2-time series, from uncorrelated process to bivariate white noise process to short memory cross-correlated process. And in all scenarios, we made 1,000 replications, sample size was 2,000, and we tried different proportions of missing data, 10%, 20%, 50, and 80. Let me explain that we did not pay attention during the generating process. So we would have, say, a pair of time series with 80%. We just use 80% here and 80% here. So the true proportion of combined missing data can be higher than 80%. And so the results are very, how can I say, the results hold for univariate, but bivariate, the proportion may be higher. As window size, we tried from 3 to 101. We use mean square error as a metric. We compare the different imputation methods and use one-step shifts for the variables to use as covariates. So what did we find with our simulations? First, we discovered that the optional imputation method does depend on the underlying structure of the process and the proportion of missing data. No surprise here. Mean-based methods like mean, CART, and PR3 PR3, which are mean-based methods, since CART estimates the conditional mean and so does the probabilistic regression trees. These methods work better for uncorrelated data and for MEA processes. When we use a different correlation structure, like autoregressive or autoregressive with moving average series, then linear interpolation and Kalman smoothing were superior. And which is very interesting, the last observation carried forward was consistently the worst performance overall. Just to remember, last observation carried forward, we just look for the last observed value and keep repeating this until the next observation it's not missing. So to answer the last question, which is about the proportion of missing, we found out that linear interpolation, Kalman smoothing, and the moving average based method, they exhibit a significant decline in performance when the proportion of missing values increase. And in the scenarios where these methods are the dominant, the tree-based methods were very comparable at a 80% missing rate. So basically, when there's too much missing data, all methods are very similar. And now our main question, do these results here, do they reflect, or these scenarios here, do they reflect on the DFI and the CCI estimation? And what we found out is that the results which we obtain with reconstructed time series are very different from the computed with the complete series. No surprises here. But the main linear decay remains observable. So we still can observe that these coefficients will have a linear decay as m increases. We may not be able to estimate the correct constant of proportionality, but the behavior itself is there. The other interesting characteristic is that the best imputation method does not necessarily yield the closer estimates to the expected values. So we cannot just say, well, since mean was better to impute, mean will also be better to estimate these coefficients. It is true, however, that imputation methods that perform well in terms of MSE tend to yield more accurate DFA estimates. So for DFA, okay, we can make this comparison. But it's interesting that LOCF, which was the worst performance in the other case, now performed pretty well for some specific scales, as 27, 81, 101, which mainly are interest. We want to understand the behavior of these coefficients as m increases. As for the trended cross correlation coefficient and this DCCA, the picture is much more complex. We don't have a single answer, say for moving average or for ARMA models, this method is the best. They depend on the window size, the proportion of missing, so it's very complex. However, again, last observation carried forward show robust performance across various settings. And we could find good results estimating these coefficients. Of course, the behavior depends on proportion of missing, window size, and correlation structure. So to give a very short answer if you want to say in practice, which method should be used? And the answer is, it depends. The choice of the imputation method should be guided by prior knowledge of the correlation structure, proportion of missing, and the window size. But we recommend to use linear interpolation since it's a very simple method. It's favorable for general purposes. Ele é reliable, consistently reliable for imputation and estimation, and it's today our best choice. This result also shows that we need to make sure that the correlation structure is taken into account when we are processing the data or imputing the data to compute these coefficients, the FA and the CCA later. So for future work, our idea is to evolve the PR3 algorithm, say using boosting or random forest, to derive asymptotic results for the FA, the CCA estimates when there are missing data, and to extend the simulations to time series with long-range dependence to understand if the limiting behavior is still can be observed when we impute the data and then compute these coefficients. Okay, that's it. Thank you. If anyone have any question.
Thank you, Tayane, so much for your presentation. I don't see any questions in the Q&A. So in the interest of time, I'm going to go ahead and finish the session. I would just like to thank our speakers once more. Tayane, Daiane, and Kelly showed us some very interesting high-level contributions to different areas of academics and statistics. And these, sorry, someone lifted their hand. I asked you that if you have any questions, please put the questions in the chat, okay? These contributions were very interesting in diverse fields, and it's very relevant to note that while working with these, well, very high level problems, these women have also been juggling a lot of the other demands of being a woman in academia, which we usually don't talk about, but I think it's very important in the context of this conference. So we have different administrative duties. They're also dealing with young motherhood, dealing with finding their space as a woman in a field that is usually very dominated by men. So I really congratulate you three for the contributions, and once more want to thank you for accepting being a part of this. Of this session. Someone raised their hand, but apparently we haven't seen the question. So I ask you if you have other questions for the speakers. We have their contact information on the website, so please go ahead and get in contact directly with our speakers. And thank you so much for everything. I'm going to stop the recording right now.